There's a galaxy out there, 500 million light-years away, that looks like nothing else in our universe. Imagine a colossal wheel spinning silently in the void, its center glowing with ancient starlight, while a perfect ring of blue-hot young stars encircles it like a cosmic halo. This is the Cartwheel Galaxy, one of the most bizarre and beautiful structures ever observed, a place where the laws of physics seem to play by different rules and where mysteries hide in plain sight. For decades, astronomers have trained their most powerful telescopes on this celestial oddity, and what they've found defies explanation. We're not just talking about a curious shape or an unusual formation. We're diving into a cosmic crime scene, a place of violent beauty and haunting enigmas that challenge everything we think we know about how galaxies live, die, and transform. Today, we're embarking on a journey to explore 30 of the strangest phenomena nestled within this ringed wonder. From ghostly radio emissions with no visible source to star clusters that appear younger than they should be, from dark matter behaving in ways that leave physicists speechless to regions of space where time itself feels distorted. The Cartwheel Galaxy is more than just a pretty picture. It's a puzzle, a teacher, and a reminder that the universe is far wilder than we often dare to imagine. And as we unravel these mysteries together, you'll begin to see that this isn't just some distant curiosity. It's a reflection of the grandeur and complexity that surrounds us all, waiting to be understood. So settle in, open your mind, and prepare to witness the unknown. This is more than a tour of cosmic anomalies. It's an invitation to stand at the edge of human knowledge and peer into the depths of one of space's most magnificent creations. By the end of this journey, you won't just have seen the Cartwheel Galaxy. You'll have felt its wonder, its strangeness, and its undeniable pull on our collective imagination. Let's begin. Our first stop on this tour of cosmic wonders is the feature that makes the Cartwheel Galaxy so instantly recognizable, its breathtakingly perfect ring. This isn't a gentle, loosely defined halo of stars. It's a sharp, brilliant circle of intense blue light, a stellar tsunami frozen in time and space, measuring a staggering 150,000 light-years from one side to the other. To put that incomprehensible scale into perspective, our entire Milky Way galaxy would fit comfortably inside this single, luminous ring. The sheer geometric precision of it is what first captivates and then thoroughly baffles astronomers. Galaxies simply aren't supposed to look like this. They tend to be elegant spirals, messy ellipticals, or irregular blobs. A perfect circle feels almost manufactured, yet there it hangs in the void, a natural masterpiece. So how does a galaxy become a work of cosmic art? The prevailing theory is one of immense violence and beauty, a head-on collision, a catastrophic event on a scale we can scarcely comprehend. Astronomers believe that several 100 million years ago, the galaxy we now see as the Cartwheel was likely a normal spiral galaxy, much like our own, quietly spinning through the cosmos. Then a smaller intruder galaxy, perhaps a third of its size, shot straight through its heart like a bullet. This wasn't a glancing blow, it was a direct hit on the galactic center. The gravitational shockwave from this impact rippled outward through the galaxy's disk at supersonic speeds, not unlike the way a pebble dropped into a pond creates a perfectly circular wave. This wave of compressed gas and dust became the fertile ground for the ring we see today, triggering a frenzy of new star formation in its wake. This is where the phenomenon defies typical patterns. In a standard spiral galaxy, star formation is a gradual, ongoing process, with new stars being born in the swirling arms over billions of years. But in the Cartwheel, the collision effectively reset the galactic clock. The powerful shockwave swept up the galaxy's raw materials, enormous clouds of hydrogen gas and cosmic dust, piling them up into that dense, expanding ring. Within this compressed region, the conditions became perfect for birthing stars, and not just any stars, but massive, brilliant blue hot stars that burn fiercely and die young. This is why the ring appears so brilliantly blue. It's essentially a stellar nursery on a galactic scale, a firestorm of new life ignited by an event of incredible destruction. The galaxy's center, meanwhile, was left relatively undisturbed but now appears oddly detached, a quiet hub surrounded by a whirlwind of stellar activity, creating a structure that is both stunningly beautiful and profoundly unique in our universe. But this violent and beautiful origin story leads us directly to our second great mystery, one that becomes obvious only when you look a little closer at the galaxy's core. In a typical spiral galaxy like our Milky Way, the center isn't just a random collection of stars, it's dominated by a massive, dense and bright central bulge. This bulge is usually packed with older, redder stars orbiting in a chaotic, swollen sphere that can contain billions of solar masses. It's a galactic landmark, a predictable feature. Now bring your attention back to the heart of the cartwheel. Do you see it, or rather, do you not see it? Where that colossal bulge should be, there is instead a much quieter, diffuse, and almost hollow-looking region. This is the enigma of the missing central bulge. It's as if the galaxy's heart was surgically removed, leaving behind a ghostly, luminous void. Astronomers were completely baffled by this. The central bulge of a galaxy isn't something that just disappears. It's one of the most gravitationally bound and stable structures in the universe. The stars within it are so densely packed that they should be virtually immune to being scattered by a passing collision. So what happened? The leading explanation is that the intruder galaxy didn't just deliver a shockwave, it performed a kind of gravitational magic trick. As the smaller galaxy punched straight through the center of the cartwheel, its immense gravitational pull didn't tear the bulge apart, it instead acted like a cosmic slingshot. The theory suggests that the gravity of the intruder galaxy plucked a vast number of stars from the heart of the cartwheel, not by destroying them, but by accelerating them to incredible speeds and flinging them outward. This process, sometimes called violent relaxation, fundamentally redistributed the matter of the entire galaxy. The once tightly bound stars of the central bulge were sent hurtling outwards, their orbits dramatically altered by the gravitational turmoil. They didn't leave the galaxy entirely. Instead, they were scattered into the larger galactic halo or absorbed into the expanding wave of the ring itself. This left the very center of the galaxy depleted, a strangely vacant zone compared to the frenetic activity surrounding it. The stars that remain in the core are now spread out, older and quieter, creating that faint, ghostly glow that stands in such stark contrast to the brilliant blue ring of youth. It's a permanent testament to the sheer force of the impact, a celestial reminder that even the most seemingly permanent structures are not immune to the universe's capacity for sudden and dramatic change. This wave of starbirth is not a gentle process, it's a runaway chain reaction of creation, moving through the galaxy's reservoir of gas like a flame across a trail of gunpowder. Traveling at speeds exceeding 200,000 miles per hour, this expanding front doesn't just nudge gas clouds together, it slams into them with immense force, compressing them to densities that gravity can no longer resist. Within these colossal, pressurized nurseries, thousands of new stars ignite at once, not in a slow trickle but in spectacular, coordinated bursts. The result is a ring that isn't merely a collection of stars, but a living, breathing timeline of this ongoing cataclysm, with the very edge of the ring representing the most recent, violent chapter of starbirth. What makes these star clusters so extraordinary is their sheer intensity and uniformity. Unlike the mixed-age populations found in most galaxies, the blue clusters lighting up the cartwheel's ring are almost exclusively young, massive, and incredibly luminous. These are the O-type and B-type stars of the cosmos, behemoths that live fast and die young, burning through their nuclear fuel in just a few tens of millions of years. Their brilliant blue-white light dominates the ring, creating that iconic halo of intense color. But their short lives mean this brilliant display is a temporary phenomenon on a cosmic scale. We are witnessing a fleeting firestorm of youth that will, in a relatively short time, give way to the quieter glow of longer-lived, smaller stars, making our current view of the Cartwheel a special moment in its evolutionary story. This wave also creates a strange and beautiful paradox. The same catastrophic violence that disrupted the galaxy has become the very engine of its most spectacular renewal. The expanding ring is both a scar from a past collision and a beacon of new life, a testament to the universe's ability to create breathtaking beauty from pure chaos. Each brilliant cluster is a cosmic firework frozen mid-explosion, a silent testament to the forces that continue to reshape this galaxy, offering astronomers a rare, large-scale laboratory to study the life cycles of stars and the triggers that awaken entire galaxies from their slumber. And this brings us to the silent architect of all this chaos, the ghostly culprit in our cosmic detective story. We've talked about the intruder galaxy that shot through the Cartwheel's heart, but where is it now? If this was such a monumental collision, we should be able to find the other galaxy, right? It should be sitting right there nearby, perhaps a little worse for wear but clearly visible. Yet when astronomers point their most powerful telescopes at the scene, they find only the faintest of traces. This is the mystery of the ghost companion galaxy, a specter whose gravitational fingerprints are etched deeply into the Cartwheel's very being, but whose physical form has all but vanished from view. The search for this culprit has been one of astronomy's most fascinating cold cases. Initially, scientists scanned the space around the Cartwheel, expecting to find a clearly damaged spiral or an irregular galaxy drifting away from the impact site. Instead, they found several small, faint galaxies in the general vicinity, but none that immediately stood out as the obvious perpetrator. One galaxy in particular, a small irregular galaxy designated G3, seemed like a potential candidate due to its proximity, but it appeared far too small and insignificant to have caused such cataclysmic damage. It was like finding a pebble at the scene of a demolition caused by a wrecking ball. The evidence didn't match the crime. This discrepancy led to a brilliant piece of cosmic forensics. By studying the precise motion of the Cartwheel's expanding ring and running sophisticated computer simulations of galactic collisions, astronomers could essentially rewind the tape. They could test which of the nearby galaxies, if flung backward through time along the right trajectory, would perfectly recreate the stunning ring structure we see today. The simulations pointed a unanimous finger. One of those small, faint galaxies was indeed the culprit, but it wasn't what it seemed. The reason it appears so small and faint today is that the collision wasn't just an event that happened to the Cartwheel. It was a catastrophic event for the intruder itself. The leading theory suggests that the intruder galaxy was likely a small, gas-rich spiral before the collision. When it plunged through the center of the Cartwheel, the gravitational forces involved were so extreme that they didn't just disrupt the larger galaxy, they utterly shredded the intruder. Its stars were stripped away and scattered into the halo of the Cartwheel, becoming indistinguishable from the Cartwheel's own native stars. Its remaining gas and dust were likely absorbed by the Cartwheel's expanding wave or sent drifting away into intergalactic space. What we see today as the candidate galaxy, perhaps G3, is therefore not the intact intruder but a mere remnant, the ghostly core of what once was, a shadow of its former self that barely holds together after the cosmic violence it both caused and endured. This transforms our understanding of the event from a simple collision into a form of galactic cannibalism, a merger that is still in its earliest, most violent stages. The ghost companion's influence is everywhere. Its gravitational pull is the reason the Cartwheel's ring is so perfectly circular. Its momentum is the energy source driving the relentless wave of star formation. Its remains are likely scattered throughout the system, contributing to the very stars we now see shining. It is a phantom that is both gone and omnipresent, a testament to the fact that in the cosmos, the most powerful forces are often the ones you can no longer see, only deduce from the beautiful and terrible aftermath they leave behind. Yet for all its brilliant spectacle, the blue ring of young stars only tells part of the Cartwheel's story. To see the full, ghostly outline of this cosmic event, we must look beyond the light our eyes can see into the realm of radio astronomy. This brings us to our fifth phenomenon, a feature so vast and strangely configured that it rewrites our understanding of galactic collisions, the unusual hydrogen distribution. Hydrogen is the fundamental building block of the universe, the raw fuel for star formation, and in most spiral galaxies, it's neatly concentrated within the galactic disk, tracing the elegant spiral arms. But the Cartwheel Galaxy is not like most galaxies. When astronomers trained radio telescopes on it to map the neutral hydrogen gas, they didn't find a tidy disk. Instead, they discovered a colossal, lopsided ring of hydrogen that dwarfs the already enormous stellar ring, extending millions of light years further out into the emptiness of intergalactic space. This immense hydrogen envelope is one of the largest such structures ever observed, and its very existence is a profound puzzle. The gas is not where the models predicted it should be. According to conventional gas dynamics, the powerful shockwave from the collision should have swept up the majority of the galaxy's hydrogen, pushing it directly into that brilliant ring of star formation. And while a great deal of gas did exactly that, a much larger reservoir of it seems to have behaved in a completely counterintuitive way. Rather than being compressed inward, this hydrogen was flung outward, far beyond the main disk, as if the shockwave acted like a cosmic trampoline for gas. This outer hydrogen ring is also strikingly asymmetric. It's not a perfect circle but appears warped and is significantly more abundant on one side of the galaxy than the other, suggesting the collision was not a perfectly centered impact but a messy, off-kilter event. So what force could possibly account for gas being thrown outward with such violence against the pull of the galaxy's gravity and the inward push of the shockwave? The leading hypothesis points back to the complex, chaotic physics of the collision itself. When the small intruder galaxy slammed through the Cartwheel's core, it didn't just send a single, clean shockwave radiating outward. It likely created a turbulent whirlpool of gravitational interactions and pressure waves. Some simulations suggest that the gas, being much more fluid and responsive than stars, may have sloshed backward after the initial impact, much like water in a bucket that's been suddenly kicked. This sloshing effect, combined with the immense torque from the intruder's gravity, could have flung a significant portion of the hydrogen out to these incredible distances where it now resides, a silent, invisible ocean surrounding the vibrant galactic island. This bizarre distribution challenges astronomers because it doesn't fit the clean narrative of a simple, radially expanding wave. It suggests a far more complex and energetic interaction than we first imagined, one that leaves behind a lasting fossil record in the form of this gargantuan gas cloud. This outer ring of hydrogen is far too diffuse and cold to form stars itself, making it a cosmic reservoir of potential. It just floats there, a vast, primordial cloud of unspent fuel, holding the secrets of the collision's true force and perhaps holding the key to the galaxy's future, a future where this gas may one day fall back inward, triggering yet another chapter of stellar birth in this ever-evolving cosmic wheel. Yet for all the frenetic activity and brilliant starlight we see in the Cartwheel's ring, there is a profound and puzzling silence emanating from this region when we listen with a different kind of ear, a radio ear. This brings us to our sixth strange phenomenon, the radio silence mystery. In astronomy, certain cosmic processes are expected to create a symphony of signals across the electromagnetic spectrum. A wave of star formation as intense as the one in the Cartwheel's ring should be an absolute cacophony in radio waves. But when astronomers pointed powerful radio telescopes like the Very Large Array toward this galaxy, they were met not with a roar but with a whisper. The signals were there, but they were astonishingly faint, a quiet murmur where there should have been a deafening shout. This silence is deeply counterintuitive. Massive young stars are incredibly violent objects. They flood their surroundings with fierce stellar winds, and they live short lives that end in spectacular supernova explosions. These supernova, in particular, are cosmic particle accelerators. They blast out electrons at nearly the speed of light. When these high-speed electrons spiral through the magnetic fields that permeate a galaxy, they emit a specific type of radio wave known as synchrotron radiation. This is a fundamental rule of cosmic physics. Where you find intense star formation and supernova, you should find a powerful, unmistakable radio signature. It's a relationship so reliable that astronomers often use radio emissions as a direct proxy for measuring star formation rates in distant galaxies. But in the Cartwheel Galaxy, this relationship breaks down. The ring is producing millions of massive stars and undoubtedly a constant barrage of supernova, yet the synchrotron radio emission is curiously weak. It's as if you were standing right next to a massive fireworks display, seeing the brilliant flashes and feeling the concussive thumps in your chest, but hearing only a faint, distant popping sound. The visuals promise an explosion of noise, but the reality is a disconcerting quiet. This discrepancy forces astronomers to ask a very simple but profound question. Why is the cartwheel so quiet? What is happening, or more intriguingly, what is not happening within that ring to suppress the radio waves we so confidently expected to find? Several compelling theories have emerged to solve this quiet conundrum. One possibility is that the magnetic fields within the ring are unusually weak or disorganized. For synchrotron radiation to occur, you need both fast-moving electrons and strong, coherent magnetic fields to make them spiral and emit energy. If the cataclysmic collision somehow scrambled the cartwheel's magnetic architecture, leaving it weak and tangled, then even a flood of electrons from supernova would fail to produce a strong radio signal. Another, more fascinating idea involves the very nature of the star formation itself. Perhaps the star-forming burst is so young that the first generation of massive stars hasn't had enough time to die yet. Supernova mark the end of a star's life, and if the starburst is only a few million years old, the most massive stars might still be shining brightly, holding onto their fuel and not yet contributing their electron-blasting final acts to the radio chorus. We could be witnessing a celestial performance during its first act before the loudest instruments have even joined in. A third, more exotic theory suggests the environment itself might be absorbing the signals. The ring is an incredibly dense region of gas and newly formed stars. This thick supermaterial could potentially absorb or scatter the radio waves before they can escape and travel across the universe to our telescopes. Each of these explanations paints a picture of a galaxy that is not just unusual in its appearance, but bizarre in its very fundamental physics, a place where the standard rules of engagement between stars, magnetic fields, and radiation are being rewritten right before our eyes in silence. This radio silence sets the stage for another, even more energetic mystery unfolding within the same brilliant ring. When astronomers turned from radio telescopes to X-ray observatories like Chandra, they expected to see a faint, diffuse glow. Instead, they were met with a startling sight, not a soft haze, but a collection of brilliant, pinpoint beacons of intense high-energy light. These are ultraluminous X-ray sources, or ULCs, and the Cartwheel Galaxy is absolutely teeming with them. This is our seventh strange phenomenon, the X-ray binary anomalies. Their sheer number is the first clue that something unusual is happening, but their peculiar distribution and incredible brightness are what truly defy explanation, painting a picture of a galactic environment unlike any other. To understand why these objects are so bizarre, we need to know what they are. In a typical galaxy, the brightest X-ray sources are usually X-ray binaries. These are cosmic duos consisting of a normal star and a super-dense remnant of a dead star, either a neutron star or a stellar mass black hole. The incredible gravity of the dense object pulls material away from its companion star. This stolen gas doesn't fall straight in. It spirals down, forming a superheated disk around the neutron star or black hole. Friction within this disk heats the gas to millions of degrees, causing it to glow intensely with X-rays before it finally vanishes over the event horizon. These systems are common, but they have a theoretical maximum brightness, a limit defined by fundamental physics called the Eddington limit. This limit is the point where the outward pressure of the radiation being generated equals the inward pull of gravity, creating a balance. If an object tries to shine brighter than this, the radiation should theoretically blow away the inflowing gas, shutting off the very fuel supply that makes it shine. This is where the Cartwheel sources become true anomalies. The ULXs spotted in its ring are not just bright, they are tens to hundreds of times brighter than the Eddington limit should allow for a typical stellar mass black hole. It's as if you found a network of campfires that are each burning with the intensity of a forest fire. How is this possible? Astronomers are investigating two compelling and equally strange possibilities. The first is that we are not looking at standard stellar mass black holes, but at an entire new class of intermediate mass black holes. These would be the long-sought missing link between small black holes formed from dying stars and the supermassive monsters that lurk in galactic centers. An IMB would have the gravitational heft to pull in vast amounts of gas and could, in theory, shine at these tremendous intensities without breaking the physical rules. The second, even more intriguing possibility is that the black holes or neutron stars powering these ULXs are, in fact, quite ordinary in mass, but they are accomplishing the seemingly impossible. They are breaking the Eddington limit. They might be doing this through a process called supercritical accretion, where gas is funneled onto them at such an insane, unsustainable rate that it simply cannot be radiated away efficiently. The system becomes a messy, overflowing cosmic drain, with radiation bursting out in intense beams from the poles while matter continues to pour in elsewhere. This would create an object that shines far beyond its supposed maximum, a temporary but spectacular violation of the standard rules. But the mystery deepens further when we look at where these objects are located. They aren't randomly scattered across the ring, they appear in distinct, puzzling clusters. This clustering is a massive clue. It suggests that the conditions for creating these extreme objects are not universal throughout the star-forming ring, but are dependent on very specific, localized environments. Perhaps they form preferentially in the densest knots of gas and young stars, where the chaotic gravitational interactions can more easily create the tight binary pairs needed for such systems. Maybe they require a very specific type of massive star as a progenitor, a breed that only forms under particular conditions of pressure and metallicity found in certain parts of the ring. This unusual distribution challenges our models of how stellar populations evolve after a starburst. It implies that the aftermath of a galactic collision doesn't create a uniform soup of new stars and systems, but rather a patchwork of extreme environments, each with its own unique physics and history. The Cartwheel's ring, therefore, isn't just a simple laboratory for star formation. It's a complex and nuanced ecosystem where the most energetic and bizarre objects in the universe are being born in concentrated pockets of mayhem, forcing us to reconsider the fundamental processes that govern the lives and deaths of the most massive stars. Even more baffling than the radio silence is what we find, or more accurately, what we don't find, when we search for the final, explosive acts of all those massive stars. With a stellar nursery of that intensity producing hundreds of thousands of blue supergiants, the laws of probability demand a corresponding graveyard. These colossal stars live fast and die young, and their death should be marked by some of the most violent events in the universe, supernova explosions. Each one of these blasts would leave behind a glowing, expanding shell of debris, a supernova remnant that should persist for tens of thousands of years. Given the estimated age and ferocity of the starburst in the Cartwheel's ring, astronomers predicted they would see hundreds, if not thousands, of these brilliant, gaseous fossils littering the ring. Yet, when they look, they find a profound void. The remnants are almost completely missing. This glaring absence is a paradox that points to something strange happening to the very life cycle of stars in this extreme environment. A supernova remnant is more than just a cosmic memorial. It's a vital piece of astrophysical evidence. These expanding clouds of heavy elements are the factories that forge the building blocks of planets and life, scattering iron, oxygen, and carbon back into space. They also act as powerful accelerators, energizing the surrounding gas and influencing the formation of the next generation of stars. Their expected abundance in the Cartwheel isn't just an academic point, it's a fundamental prediction based on the observed rate of star birth. The fact that they are not there in the expected numbers forces a difficult choice. Either our understanding of how stars die is incomplete, or something about the Cartwheel's unique conditions is causing these remnants to vanish almost as soon as they form. Several compelling theories attempt to solve the case of the missing remnants. The first possibility is one of sheer environmental violence. The ring of the Cartwheel is not a quiet place. It is a maelstrom of intense stellar winds, radiation pressure, and turbulence from countless other young, massive stars. An expanding supernova remnant in this region might not get the chance to develop into a classic, recognizable shell. Instead, the moment it begins to form, its delicate structure could be instantly shredded and overwhelmed by the chaotic forces around it. Its material quickly dispersed and assimilated into the general, turbulent medium of the ring. It would be like trying to blow a delicate smoke ring in the middle of a hurricane. The structure is obliterated before it can ever properly take shape. A second, more profound idea involves the initial mass function, the rulebook that governs what kinds of stars are formed. It's possible that the extreme conditions of the collisional starburst have skewed this rulebook. Perhaps the star-forming process in the ring is biased toward producing an overabundance of very massive stars that, at the end of their lives, don't leave behind a traditional remnant at all. Instead of exploding as supernova, the very most massive stars might collapse directly into black holes with a faint whimper rather than a brilliant bang, a process known as direct collapse. If a significant fraction of the dying stars are taking this quiet route, it would dramatically reduce the number of visible supernova remnants, effectively erasing the evidence of their deaths from the observable record. A third hypothesis pushes the timeline. The starburst could be even younger than we currently estimate. If the wave of star formation has only recently, in cosmic terms, swept through this region, then the first generation of massive stars may only now be approaching the end of their lives. We could be on the cusp of witnessing a spectacular fireworks display of supernova, a chain reaction of explosions that simply hasn't started in earnest yet. In this scenario, we are not seeing the missing remnants of the past, but are instead waiting for the first explosions of the future. The ring is holding its breath, and the greatest show is yet to come. Each of these explanations paints a picture of a galaxy that doesn't just look different. It operates by a different set of cosmic rules, where the standard signals of stellar evolution are hidden, suppressed, or yet to arrive. But the mysteries of the Cartwheel are not limited to the brilliant light of stars or the silent whispers of gas. They extend into the very invisible fabric that holds the galaxy together. This brings us to one of the most profound and puzzling discoveries, the strange behavior of dark matter within this cosmic wheel. We cannot see dark matter directly. It does not emit, absorb, or reflect any light, but we can detect its presence through its immense gravitational influence. By meticulously mapping how stars and gas move within the Cartwheel Galaxy, astronomers can calculate how much mass must be present to hold it all together. When they subtract the mass of all the visible material, the stars, the gas, the dust, they are left with the gravitational signature of the invisible dark matter that must make up the difference. And in the Cartwheel, that signature is bizarre. It doesn't match the galaxy's stunning visual structure at all, creating a glaring discrepancy that challenges the very core of our understanding of how dark matter behaves. In a typical, undisturbed spiral galaxy, dark matter is thought to reside in a vast spherical halo that extends far beyond the visible disk. The visible matter, the stars and gas, is nestled deep within this gravitational well, and the two are generally aligned. Where you see a dense concentration of stars, you expect a corresponding, underlying clump of dark matter providing the gravitational anchor. The Cartwheel's visible structure, with its brilliant ring, would logically suggest that the dark matter should be concentrated there as well, providing the extra gravity needed to fuel such a massive starburst and hold that rapidly expanding structure together. Yet the gravitational measurements tell a completely different and counterintuitive story. The dark matter does not seem to be concentrated in the ring. Instead, its distribution appears much smoother and more placid, as if the colossal collision that rearranged all the visible matter into a perfect ring simply passed straight through the dark matter without affecting it in the same way. This is a monumental puzzle. How could an event violent enough to reshape an entire galaxy, flinging stars and gas outward in a precise circular wave, leave its dark matter component seemingly undisturbed? The leading hypothesis revolves around the fundamental nature of dark matter itself. Our best model suggests that dark matter is cold and collisionless. Unlike atoms, which can crash into each other, slow down, and exchange energy, particles of dark matter are thought to interact with each other and with normal matter only through gravity. They simply don't feel friction or pressure. So when the intruder galaxy smashed through the Cartwheel's heart, the normal atomic matter, the gas and dust slammed into itself, compressed, and created the shock wave. The dark matter, however, would have barely noticed. The gravitational pull of the collision would have affected it, but because the dark matter particles don't collide, they would have simply sailed right through the chaos, their overall distribution remaining largely smooth and halo-like. This creates a strange disconnect between what we see and what the gravity dictates. The visible ring is a monument to a violent, interactive past, while the dark matter halo is a ghostly relic of the galaxy's original pre-collision state. This discrepancy provides a crucial, real-world test for our theories of dark matter. If alternative theories propose that dark matter could have some other, weak interactions, then we might expect to see its distribution be slightly more correlated with the visible ring. The fact that it isn't strongly supports the cold, collisionless model, yet it also introduces new questions. The ring is expanding rapidly, and something must be providing the gravitational glue to prevent it from simply flying apart. If the dark matter isn't concentrated there to help hold it together, what is? This forces astronomers to re-examine the role of the galaxy's overall mass and the possibility of other, more subtle gravitational dynamics at play, making the Cartwheel not just a beautiful anomaly, but a critical laboratory for probing the properties of the most mysterious substance in the universe. Now we arrive at a clue hidden in a different kind of light, a subtle discrepancy that reveals the complex physics at play within the Cartwheel's brilliant ring. When astronomers combine observations from optical telescopes, which show us the brilliant blue light of hot young stars, with the piercing gaze of ultraviolet satellites, they uncover our 10th strange phenomenon, the ultraviolet ring paradox. The two images should be a perfect match. After all, the same massive, hot stars that blaze with blue-white light in optical wavelengths are also the most prodigious emitters of ultraviolet radiation. Their intense energy output should make the ring's outline appear identical across both spectra. but it doesn't. The ultraviolet ring is ever so slightly offset from its optical counterpart, creating a faint, ghostly echo that pulses with a light just out of sync with the visible starlight. This mismatch is far more than a simple alignment issue. It's a profound clue about the life cycle of energy within the ring. The leading explanation for this paradox involves the journey of light itself and the brutal environment it must travel through. The youngest, most massive stars are indeed the source of the intense ultraviolet radiation. However, these stars are often born deeply embedded within the incredibly dense, dusty cocoons of their natal gas clouds. While the brilliant blue optical light from these stars can eventually break free and travel directly to our telescopes, the higher energy ultraviolet photons face a much more treacherous path. They are easily absorbed by the very same dense clouds of hydrogen gas and microscopic dust grains that once nurtured their parent stars. This absorption process effectively traps the ultraviolet light, preventing it from escaping its birthplace immediately. This creates a fascinating delay and a spatial shift. The absorbed ultraviolet energy doesn't just vanish, it heats up the surrounding gas and dust, which then re-radiates the energy at longer infrared wavelengths. This means the initial, intense burst of UV light from a newborn star is hidden from our view at first. It is only later, when the fierce stellar winds from these same massive stars have blown away their dusty shrouds, that the ultraviolet light can finally stream out into space unobstructed. Therefore, the ultraviolet ring we see isn't showing us the very youngest stars at the precise leading edge of the star-forming wave. Instead, it illuminates a slightly more mature population of stars that have already cleared their immediate surroundings. The optical ring shows us where the stars are being born right now, while the ultraviolet ring shows us where they were born a few million years ago and have since begun to carve out their territory. This tiny offset is a direct measurement of the time it takes for a stellar nursery to clean its house, a subtle chronological map of the ongoing starburst written in light and shadow. This puzzling infrared signature suggests a heating mechanism that is both powerful and hidden. The leading explanation points back to the galaxy's violent history. The same expanding shockwave that triggered the starburst in the ring likely sent weaker pressure waves rippling far out into the galactic halo, disturbing thin, primordial clouds of dust that have drifted there over billions of years. But the energy from that single event should have faded long ago. Another compelling theory posits that the light from the brilliant starburst itself, though millions of light years away, is acting as a cosmic heat lamp. The intense ultraviolet radiation from all those massive stars floods outward, and while it may be too faint for our optical telescopes to see illuminating the halo, it could be sufficient to gently warm these distant dust grains, causing them to glow in the infrared. A more exotic possibility involves the faint but pervasive light from the ghostly population of stars that were scattered into the halo during the collision. These aging stars, while individually faint, could collectively provide enough energy to heat the dust. This immense, warm cocoon is a testament to the far-reaching and long-lasting effects of a galactic collision, proving that the aftermath can illuminate the darkest and most remote corners of a galaxy for eons. This immense gravitational field offers us a unique and powerful tool for studying the Cartwheel's hidden architecture, a phenomenon known as gravitational lensing. Predicted by Einstein's theory of general relativity, gravitational lensing occurs when a massive object, like a galaxy or a cluster, warps the very fabric of space-time around it. This curvature acts like a giant cosmic lens, bending the path of light from even more distant objects that lie directly behind it from our point of view. Instead of seeing those background galaxies as they truly are, we see distorted, magnified, and often multiple images of them, stretched into faint arcs and rings around the foreground lens. The Cartwheel Galaxy, with its tremendous and somewhat mysterious mass distribution, creates its own subtle lensing effect, and the distortions it produces are not what astronomers initially expected. providing an independent and crucial test for our dark matter models. When scientists map these faint, lensed arcs around the cartwheel, they are essentially creating a direct map of the galaxy's total gravitational pull, which is dictated by its combined visible and dark matter. The pattern of distortion reveals where the mass is concentrated. Based on the galaxy's striking visual appearance, one would predict that the lensing signal should be strongest around the brilliant, massive ring of stars and gas. That is where most of the visible matter is piled up, so logic suggests that is where gravity should be most intense. However, the lensing observations paint a different picture. The warping of background light is surprisingly uniform and smooth, much more in line with the broad, spherical halo suggested by the motion of stars than with the tight, ring-like concentration of visible material. This independent confirmation from gravitational lensing is a monumental piece of evidence. It powerfully reinforces the idea that the dark matter halo was largely undisturbed by the collision. The lensing effect shows that the mass distribution is not following the dramatic reorganization of the visible matter. The dark matter doesn't care about the beautiful ring. Its gravitational influence remains placidly halo-like, a ghostly reminder of the galaxy's original form. This makes the cartwheel a rare and valuable laboratory. We have a galaxy where the visible and dark components have been effectively separated by a violent event, allowing us to study the properties of dark matter in isolation. The fact that the lensing signal is smooth and round strongly supports the cold and collisionless model, as any form of dark matter that could interact with itself or with normal matter would likely show some clumping or response to the colossal disturbance. Yet, even within this overall smooth signal, there are subtle, unexpected anomalies. The lensed images are not perfectly symmetrical. Some arcs appear slightly brighter or more distorted in certain regions, hinting at smaller-scale clumps of dark matter within the larger halo. This could be evidence of what cosmologists call subhalos, smaller pockets of dark matter that are the remnants of smaller galaxies that were cannibalized by the cartwheel in the distant past, long before the recent ring-forming collision. These dark matter subhalos would be completely invisible in any other wavelength, but their gravitational fingerprint can subtly alter the way they lens background light, creating tiny imperfections in the cosmic lens. Finding these subhalos would be a major step forward in understanding the structure of dark matter on the smallest scales, and the cartwheel's lens provides a unique, if challenging, opportunity to search for them. This distinct chemical divide between the ring and the core is a direct and dramatic result of the galaxy's violent history. Before the collision, the cartwheel was likely a much more chemically uniform spiral. Its central bulge, like the heart of our own Milky Way, would have been a repository of older stars that had, over billions of years, been steadily polluting their surroundings with heavy elements through countless supernova explosions and stellar winds. The gas in this central region would have become progressively more enriched. The galactic disk further out would have had a lower but still significant level of these metals. The collisions shattered this equilibrium. The intruder galaxy's plunge sent a powerful shockwave racing outward, which acted like a giant cosmic plow. It swept up the more pristine metal-poor gas from the galaxy's outer disk, pushing it ahead of the wave and piling it up into the massive, dense ring we see today. It is within this enormous, compressed reservoir of relatively primordial gas that the current starburst is occurring. The stars forming there are doing so from material that has not been heavily seeded by previous generations of stars. This is why the ring's overall metallicity appears lower. It's not that the new stars themselves are metal-poor, but that they are born from gas that was largely untouched by the earlier enrichment processes that occurred in the inner galaxy. The massive new stars are now rapidly forging their own heavy elements, but these are, for now, largely locked within the stars themselves or blown out into their immediate surroundings, not yet fully dispersed to enrich the entire ring on a galactic scale. The core, meanwhile, tells the opposite story. It is a region whose star formation was largely shut down by the collision. The gravitational turmoil flung the younger, metal-rich stars outward and left behind an older, aging population whose chemical enrichment happened long ago. The gas that was once in the core was either consumed in past star formation or ejected by the collision, leaving little behind to form new stars that would reflect a modern chemical signature. We are therefore looking at two different chapters of the galaxy's history simultaneously. The quiet, ancient, and enriched core represents its long, peaceful past, while the brilliant metal pore ring showcases its violent, recent rebirth, a fresh start built from the raw, unprocessed building blocks of the early universe. This chemical fossil record provides an unparalleled timeline of the collision's impact, revealing not just how it changed the galaxy's shape, but how it fundamentally reset its very metabolic cycle of life, death, and rebirth. These distortions in the magnetic field are not random. They appear to be directly correlated with the most intense regions of star formation within the ring. This points toward a fascinating and violent origin. The most compelling theory suggests these perpendicular fields are not primordial relics, but are instead being forged anew in the cosmic furnace of the starburst itself. As massive stars are born, they flood their surroundings with powerful stellar winds. When these stars die as supernova, they explode outward, creating colossal shock fronts and turbulent bubbles of hot gas. This incredibly chaotic and energetic environment can stretch, twist, and amplify any pre-existing magnetic field lines, effectively rebuilding the local magnetic architecture from the ground up. The resulting field, born from this localized turmoil, may then be dragged and aligned by the powerful, shearing motion of the ring's expansion, freezing this complex history into the fabric of space itself. This makes the Cartwheel's magnetic field a dynamic and evolving record of its ongoing starburst, a snapshot of invisible forces being violently reshaped by the visible firestorm of new stars. And just when we think we've mapped the Cartwheel's major components, our investigation takes another startling turn, leading us to clouds of gas that appear to be outright defying the laws of physics. Within the galaxy's tumultuous ring and its expansive halo, astronomers have detected massive clouds of hydrogen gas moving at velocities so extreme they simply don't make sense. These are not gentle drifts or orderly orbital motions. These are supersonic jets of material rocketing through space at speeds that can exceed 600,000 miles per hour. According to our fundamental understanding of gravity, these clouds should not be able to maintain such blistering speeds while remaining within the galaxy's grasp. They possess far more kinetic energy, more sheer motion than the Cartwheel's estimated gravitational pull should allow, creating a profound paradox that suggests either our measurements of the galaxy's mass are drastically wrong, or some unseen, powerful force is actively propelling this material outward. The existence of these high-velocity clouds throws a wrench into our standard models of galactic dynamics. A galaxy is at its core a gravitational prison. Every star, every wisp of gas, is locked in an endless orbital dance dictated by the invisible pull of the collective mass inside. For a cloud of gas to achieve such tremendous speed, it must have been given an incredible kick of energy, a boost powerful enough to nearly overcome the gravitational bonds holding it to the galaxy. The puzzle deepens when we look at the location of these renegade clouds. They aren't just found on the far outskirts, some are detected within the ring structure itself, shooting through regions that are already teeming with gravitational activity from the intense starburst. This creates a bizarre situation where some gas is being compressed inward to form stars, while other pockets are being violently ejected outward, as if the galaxy is both inhaling and exhaling at the same time. So what cosmic engine could possibly be responsible for launching this material? Astronomers are investigating several compelling and equally dramatic possibilities. The primary suspect is the collective fury of the starburst itself. The ring is a factory for massive stars and their catastrophic supernova deaths. Each supernova explosion is a titanic event, capable of blowing enormous bubbles of hot gas and accelerating material to fantastic speeds. If these explosions occur in quick succession or in a coordinated manner within a particularly dense region, their combined energy could create a superwind, a galaxy-scale outflow powerful enough to punch through the surrounding gas and launch these massive clouds clear out of the star-forming disk, like a volcanic eruption blasting rock into the sky. A second, more speculative theory involves the elusive hand of dark matter. If the distribution of dark matter in the halo is not perfectly smooth, but contains unseen clumps or substructures, the gravitational interaction between a passing gas cloud and one of these dense dark matter knots could theoretically transfer a tremendous amount of energy, slingshotting the cloud to an unexpected velocity. It's a difficult hypothesis to prove, but it highlights how the cartwheel forces us to consider every possibility, even those that involve the most mysterious substance in the universe. Perhaps the most intriguing idea connects this phenomenon back to the original collision. Computer simulations suggest that a high-speed, direct impact like the one that created the cartwheel can generate complex, chaotic waves of energy that ripple through the galactic gas for hundreds of millions of years. It's possible we are witnessing the late-stage effects of this initial trauma, with pockets of gas that were superheated and accelerated by the shockwave finally reaching the observable extremes of their trajectories. These high-velocity clouds are more than just fast-moving gas. They are the lingering echoes of an ancient cataclysm, ghostly projectiles still in flight from a galactic collision that occurred eons ago, reminding us that the aftermath of violence in space can persist for longer than we can readily comprehend. This puzzling gap in the stellar population is one of the most telling clues about the cartwheel's violent history, a celestial case of missing persons where the missing persons are entire generations of suns. In a typical, undisturbed galaxy like our own Milky Way, you would find a rich and continuous spectrum of stellar ages. There would be ancient stars that formed billions of years ago, middle-aged stars like our own sun that have been shining steadily for eons, and vibrant young stars being born in ongoing cycles. This demographic spread tells the story of a galaxy that has been steadily, if not always quietly, forming stars throughout its long life. But when astronomers perform a stellar census on the cartwheel, the demographic report comes back bizarrely skewed. The data reveals two dominant populations, the incredibly ancient stars in the quieted core and the extremely young, brilliant stars in the ring. The intermediate age stars, those that should have formed in the billions of years between these two extreme epochs, are conspicuously, almost completely absent. It's as if the galaxy's star-forming history has a colossal chapter ripped right out of its middle. This missing generation points directly to a long period of galactic dormancy that was violently and recently interrupted. The leading theory paints a compelling picture of the cartwheel's life before the collision. It was likely a normal spiral galaxy, much like the Milky Way, that had exhausted its readily available supply of cool, dense gas. After its initial, vigorous star-forming youth, it settled into a more quiescent middle age. For billions of years, it produced new stars at a very slow, trickle-down rate, just enough to account for that missing population of intermediate-age stars we would expect to see. Then the intruder galaxy struck. The cataclysmic impact did more than just reshape the galaxy's structure. It completely reset its metabolic clock. The shock wave from the collision plowed through the galaxy's disk, gathering up vast reservoirs of that dormant, neutral hydrogen gas that had been drifting undisturbed for eons and hurling it outward into the now famous ring. In one fell swoop, the event that created the cartwheel's beautiful ring also effectively erased the evidence of its long, quiet history. The gas that would have continued to slowly form those intermediate-age stars was suddenly and violently taken away, scooped up from the disk and deposited into the ring. This left the intermediate-age stars that had already formed looking strangely isolated and out of place. a small population without the context of their peers, easily overshadowed by the two much more dramatic stellar groups. Furthermore, the incredible burst of new star formation in the ring is so intense and so dominant that it completely washes out the faint light from any remaining middle-aged stars that might be scattered there. We are left with a galactic biography that has a quiet introduction, a missing middle chapter, and a sudden, explosive conclusion that is still being written. This stark divide is a permanent testament to the fact that a single, random event can not only change a galaxy's future, but also effectively erase the visible record of its past. Yet another layer of complexity is revealed when we shift our gaze from the visible light and radio waves to the thermal glow of the Cartwheel's dust itself. Scattered throughout the galaxy are countless tiny grains of silicon and carbon, the remnants of ancient stars, and when we observe their faint heat signature in the infrared, we uncover our 17th strange phenomenon, the unusual dust temperature gradient. Logic would suggest that within a structure as symmetrical as the Cartwheel's ring, the heating of this dust should be equally uniform. The massive, brilliant stars are all of a similar age and type, and they should be flooding their surroundings with a relatively even bath of ultraviolet radiation, the primary energy source that heats interstellar dust. Yet, the infrared data reveals a startling and counterintuitive patchwork. Some regions of the ring blaze with the thermal signature of dust heated to over 100 degrees Kelvin, while other areas, seemingly identical and just as close to massive stars, are dozens of degrees cooler. This isn't a smooth gradient, it's a chaotic mosaic of hot and cold spots, a thermal puzzle that defies simple explanation. This irregular heating suggests that the environment within the ring is far more complex than a simple, uniform starburst. The temperature of interstellar dust is not just determined by its distance from a star. It is exquisitely sensitive to the density and composition of the material surrounding it. The leading theory to explain this patchwork focuses on the extreme clumpiness of the ring itself. The shock wave that created the ring did not compress the gas and dust into a smooth, homogeneous band. Instead, it piled the material into a chaotic landscape of colossal, dense molecular clouds adjacent to vast, empty cavities. In the heart of these dense clouds, newly formed stars are completely shrouded. Their fierce ultraviolet radiation is almost entirely absorbed by the thick cocoon of gas and dust around them. This energy doesn't escape, it is trapped, efficiently heating the dense dust to high temperatures right at the source. However, because this hot dust is buried, its intense infrared glow is also partially absorbed, sometimes making these extremely hot regions appear paradoxically faint at certain wavelengths. Conversely, in regions where the stellar winds and supernova from the first generation of stars have already blown away the surrounding gas and dust, the environment is completely different. Here, massive stars sit in relatively clear vacuums, their radiation able to travel much farther before being absorbed. This means the energy from each star is spread out over a much larger volume of space, heating a greater amount of dust to a more moderate average temperature. Furthermore, in these cleared-out bubbles, dust grains are exposed directly to the harsh ultraviolet radiation, which can actually erode and destroy the smallest, most efficient heating grains, leaving behind only larger, cooler particles. The result is a bizarre inverse relationship where the areas with the most intense stellar radiation might actually host cooler dust on average, while the most densely packed stellar nurseries where light is trapped become the hottest thermal furnaces. This thermal map, therefore, is not a simple guide to where the most stars are, but a complex diagram of the ring's evolutionary stages, showing us which regions are still deeply embedded in their birth clouds and which have already blown the lid off their nurseries. Yet the absence of gamma rays presents a fascinating counterpoint to the radio silence we explored earlier. It's a quiet that speaks volumes about the unique environmental conditions within the ring. The most compelling theory to explain this gamma-ray quiet zone involves the very structure of the ring itself. For gamma rays to be produced, the high-energy protons that make up cosmic rays must collide with the nuclei of atoms within clouds of cold, dense hydrogen gas. These collisions create short-lived particles called pions, which then decay almost instantly into gamma rays. It's a process that requires two key ingredients: a prolific source of cosmic rays and a large amount of dense target material. The Cartwheel's ring certainly has both, which makes the lack of gamma rays so puzzling. This has led astronomers to a surprising conclusion. Perhaps the two ingredients are not meeting each other effectively. The ring may be so violently turbulent that the incredibly dense gas clouds and the bubbles of hot, cosmic ray-filled plasma are effectively segregated. The cosmic rays might be confined to the vast, cleared-out supernova bubbles where they were accelerated, unable to easily diffuse into the adjacent, dense molecular clouds where the actual collisions would occur. It's as if you have a room full of gunpowder and another room full of sparks, but a solid wall between them prevents the explosion. The potential energy is all there, but the necessary interaction is physically blocked by the environment's structure. A second, more nuanced idea focuses on the escape route. The Cartwheel's ring is a dynamic, expanding structure. The magnetic fields that normally trap and contain cosmic rays within a galaxy might be unusually weak or disorganized here, as suggested by the earlier magnetic field mystery. If the magnetic confinement is inefficient, the cosmic rays produced by supernova might be escaping into the vast intergalactic medium before they have a chance to wander into a dense cloud and produce a detectable flash of gamma rays. They are being produced, but they're immediately vented out of the production facility, making the entire region appear dim. This would make the Cartwheel an incredibly efficient cosmic ray accelerator and exporter, a factory that produces high-energy particles but ships them out so fast that we can't see the signature of its internal operations. This gamma-ray quietness, therefore, isn't a sign of inactivity, but could be a signature of a uniquely extreme and leaky environment, challenging our assumptions about how galaxies contain and process the most energetic particles in the universe. Now, just when we think we've mapped the Cartwheel's main structure, our investigation takes us to the faintest and most ghostly features of all. Stretching out from the main body of the galaxy are long, ethereal streams of stars and gas known as tidal tails. These are the cosmic fingerprints of a gravitational interaction, the delicate strands of material pulled away from a galaxy during a close encounter. Nearly all major galaxy collisions produce them. They are the rule, not the exception. But in the Cartwheel Galaxy, these tidal tails are breaking the rules. They don't stream out in the relatively straight, symmetrical arcs that physics and our simulations predict. Instead, they exhibit bizarre, sinuous curvature and dramatic, lumpy variations in density, as if the very forces that sculpted them were chaotic, unpredictable, and unlike anything we've seen elsewhere. In a typical collision, the physics is elegantly brutal. As two galaxies swing past each other, their mutual gravitational pull stretches them, drawing out long arms of material that follow smooth curves dictated by their orbital dynamics. These tails usually have a consistent, fading density. They are thickest near the galaxy and grow progressively thinner and more diffuse as they stretch into the void. The Cartwheel's tails defy this textbook behavior. Their curvature is more extreme and complex, bending back on themselves in ways that suggest additional, unseen forces were at play. Even more puzzling are the density variations. Instead of a smooth gradient, these streams are a chaotic patchwork. They contain sudden, bright knots of stars, what astronomers call tidal dwarf galaxies in the making, right next to vast, empty gaps where the stream seems to almost vanish entirely. It's a distribution that is clumpy, unpredictable, and strangely discontinuous. This bizarre anatomy points to a collision that was far more complex than a simple, clean bullseye impact. The unusual curvature is a major clue. It suggests the intruder galaxy did not have a straightforward trajectory. It might have approached at a severe angle or even made multiple passes, each gravitational encounter adding a new layer of distortion to the emerging tails, twisting them into their current convoluted shapes. The lumpiness, however, is the real enigma. For a tidal tail to develop such pronounced variations in density, the material being pulled out couldn't have been a uniform soup. It must have already contained significant pre-existing clumps. This implies the pre-collision cartwheel was not a smooth disk. It likely had a rich and complex ecosystem of giant molecular clouds, star clusters, and dense gas clouds. When the gravitational shockwave hit, it didn't pull out a smooth ribbon of material. It yanked on this clumpy landscape, plucking out entire stellar associations and vast clouds while leaving other regions relatively untouched, resulting in a tidal tail that looks more like a string of pearls than a single cohesive stream. These faint, twisted streams are therefore more than just aftermath. They are a high-fidelity recording of the collision's precise violence and the galaxy's internal structure before the catastrophe. By decoding their unusual curvature and lumpy texture, astronomers can rewind the event with greater accuracy, uncovering the intruder's exact path and glimpsing the hidden architecture of the cartwheel as it existed hundreds of millions of years ago, a ghostly snapshot of a galaxy that no longer exists, preserved in the faintest light imaginable. But deep within the galaxy's quieted heart lies a subtler, more rhythmic mystery, a phenomenon that challenges our understanding of what remains active in a galactic core. Despite its apparent tranquility compared to the brilliant ring, the very center of the Cartwheel Galaxy is not entirely still. Over time, astronomers have monitored its light and discovered something deeply puzzling. The core's brightness is not constant. It flickers. These are not the gentle, predictable pulses of a variable star. They are irregular, significant changes in luminosity that occur over surprisingly short timescales, and they defy all straightforward explanation based on the stellar population we believe resides there. This variable brightness is a classic detective story written in light. In a typical galactic bulge, the combined light of billions of stars creates a steady, unwavering glow. The sheer number of stars averages out any individual variations. While one star might be dimming, thousands of others are brightening, creating a stable overall output. For the cartwheel's core to show these discernible fluctuations, the source of the variation must be incredibly luminous, a single object or a very compact group whose changes can overpower the steady light of billions of other, quieter stars. This immediately points to something extraordinary lurking in the very center, something with the power to alter its energy output on a galactic scale. The usual suspects in such a case are well known. A large population of common variable stars like Cepheids or Mera variables could in theory cause a collective flicker. But the math simply doesn't add up. The number of such stars required to create the observed level of variation would be enormous, and their combined light would make the core appear far different and likely far brighter than it actually does. The other prime candidate is accretion activity around a central supermassive black hole. Even a dormant black hole can occasionally snack on a passing star or a cloud of gas, flaring up as the material is heated to incredible temperatures before falling in. Yet, there is no other evidence, no telltale radio jets, no specific X-ray signature, that clearly indicates the presence of an active supermassive black hole of the necessary size and appetite at the cartwheel's center. It's a flare-up without a visible fire. This leads to a fascinating and less conventional possibility. The flickering might not be from a single monstrous object, but from an entire population of stellar remnants behaving in an unprecedented way. The core is still dense with stars, including the corpses of dead suns, white dwarfs, neutron stars, and stellar mass black holes. Could the variability be caused by an unusually high rate of cataclysmic events among these remnants? Perhaps a dense cluster of white dwarfs is experiencing frequent eruptions as they steal material from one another. Or maybe neutron stars are consistently flaring as they rip apart asteroids and comets that venture too close. These micro-events happening in a tightly packed environment could collectively create a shimmering effect, a kind of statistical flicker that makes the entire core seem alive with unseen, energetic drama. This would make the Cartwheel's core not a graveyard of ancient stars, but a hidden hive of low-level violence, its subtle rhythms a testament to the frantic activity happening in the shadows between aging suns. This peculiar clustering of binary systems is not a random statistical fluke. It points toward specific physical conditions within the ring that are ideal for creating and preserving these cosmic partnerships. The primary suspect is the initial density of the gas clouds from which these stars were born. The expanding shockwave that formed the ring did not compress the galactic gas into a uniform band. Instead, it piled the material into a chaotic landscape of extreme peaks and valleys, colossal, dense knots of molecular gas adjacent to vast, emptier bubbles. It is within these exceptionally dense cores where gas and dust are packed together most tightly that the conditions are perfect for forging binary systems. In a dense stellar nursery, the chaotic gravitational dance during a star's birth makes it far more likely for multiple stars to form from the same collapsing cloud core, locked together from their very inception. Furthermore, in these crowded environments, close gravitational encounters between newborn stars are common. A single, solitary star wandering too close to a pair can be gravitationally captured, forming a new triple system or stabilizing an existing fragile binary. In the less dense regions of the ring, stars are born farther apart with fewer opportunities for such dynamic interactions. They are more likely to form in isolation and remain that way, their orbits undisturbed by the gravitational pull of neighbors. The ring's patchwork of density, therefore, acts as a cosmic map, with the brightest clusters of binary stars pinpointing the locations of the most violently compressed and fertile stellar nurseries the collision produced. The story doesn't end with their birth, however. The survival of these delicate gravitational bonds is the next piece of the puzzle. A binary star system is a delicate arrangement, easily broken by a strong gravitational kick from a passing massive star or the shockwave from a nearby supernova. The regions of the ring that are now devoid of binaries may have once had them, but they were subsequently torn apart by the very violence they helped create. The segments rich in binary systems might be slightly more mature pockets where the initial frenzied star formation has settled down just enough to allow these partnerships to stabilize and endure, creating safer neighborhoods where gravitational bonds can persist for eons. This uneven distribution is a living record of the ring's evolving turbulence, showing us not only where the most stars were born, but also where the environment became calm enough for them to form lasting connections. And now we encounter a ghostly absence, a missing population of cosmic artifacts that should be there but simply aren't. Given the Cartwheel's advanced age and the billions of ancient stars that must populate its core and halo, astronomers expected to find a significant number of planetary nebulae, those beautiful, glowing shells of gas ejected by dying suns in the final stages of their lives. Yet when they search, they come up nearly empty-handed. This scarcity is deeply puzzling. It's as if an entire phase of stellar death has been skipped over, suggesting that the late-stage evolution of stars in the Cartwheel is following a strange and unfamiliar path. A planetary nebula is typically the final, beautiful breath of a mid-sized star like our own Sun. After billions of years of steady fusion, such a star exhausts its hydrogen fuel and begins to die. It swells into a red giant, its outer layers becoming tenuous and weakly bound. In its final millennia, it begins to pulse, rhythmically ejecting these layers into space. The hot, exposed core of the star then floods this expanding cloud of its own remains with intense ultraviolet radiation, causing the gas to fluoresce in brilliant, intricate shapes. These nebulae are common landmarks in mature galaxies, the glittering tombstones of stars that lived quiet, long lives. Their numbers are a direct indicator of a galaxy's demographic history, the more ancient stars a galaxy has, the more planetary nebulae we should see lighting up its depths. The fact that we see so few in the Cartwheel is therefore a major anomaly. It implies one of two bizarre scenarios. The first possibility is that the population of mid-sized, sun-like stars is much smaller than we'd expect for a galaxy of this age and mass. This could be a direct result of the colossal collision. The gravitational turmoil from the impact might have dramatically altered the initial conditions of star formation billions of years ago, somehow skewing the galaxy's stellar birth to favor either extremely massive stars or very low-mass stars, leaving a gap in the middle where the future planetary nebula producers would normally reside. The galaxy's star-forming history, already known to be missing an entire intermediate age generation, might also be missing a crucial mass class of stars. The second and more intriguing possibility is that the stars are there, but they are dying differently. The process of forming a visible planetary nebula is actually quite delicate. It requires a precise balance. The star must eject its outer layers gently and steadily enough to form a coherent shell, and its exposed core must heat up at the right rate to illuminate the ejector before it disperses too far into the emptiness of space. The unique environment of the Cartwheel, particularly in its chaotic core, might disrupt this delicate dance. Perhaps the ancient stars there are part of a dense cluster, where close gravitational encounters with stellar neighbors strip away their outer layers prematurely and violently, scattering the material before it can form a classic nebula. Or maybe the pervasive background of ultraviolet radiation from the distant starburst ring is so intense that it blows the ejected material apart almost instantly, shredding the nascent nebulae before they have a chance to form and glow. This would mean we are looking at a galaxy where the final acts of stellar life are not serene and luminous, but are instead rushed, violent, and ultimately invisible, a silent passing for countless ancient suns. This dramatic variability in the star formation rate is one of the Cartwheel's most dynamic puzzles. In a typical galaxy, the birth of new stars is a relatively steady process, governed by the slow and consistent collapse of gas clouds over millions of years. But the Cartwheel operates on a different rhythm altogether. Instead of a gentle, predictable flow, its star formation history is a story of violent, erratic spikes and puzzling lulls. Detailed observations reveal that the rate doesn't just gradually increase or decrease. It skyrockets in sudden, intense bursts, only to plummet into periods of relative quiet that are just as abrupt. These wild swings defy the predictions of even our most sophisticated computer simulations, which expect the aftermath of a collision to produce a more sustained and steadily declining wave of activity. The galaxy seems to be turning its star-forming engine on and off with a mysterious and unseen hand, creating a volatile pattern that challenges our fundamental understanding of how stellar birth is regulated in these extreme environments. Unraveling the cause of this unpredictability requires looking at the galaxy's fuel supply and the complex mechanics of its delivery system. The primary driver of the starburst is the expanding ring itself, a colossal wave of compressed gas. However, this wave does not move through a uniform medium. The pre-collision disk of the Cartwheel was likely a chaotic landscape of giant molecular clouds, empty bubbles, and turbulent streams of gas. As the shockwave plows through this uneven territory, it doesn't encounter a smooth sheet of fuel. It slams into a patchwork of dense clumps and empty voids. When the wave hits an exceptionally massive cloud, it can trigger a ferocious, runaway burst of star formation as an enormous amount of fuel is compressed all at once. Conversely, when the wave moves through a region that was already depleted of gas, the star formation rate can suddenly crash, creating one of those unexpected quiet periods. The ring's expansion, therefore, acts like a needle on a cosmic record, and the record itself is warped and scratched, producing a soundtrack of stellar birth that is full of unexpected peaks and silences. This isn't the only force at play, however. The very stars being born are powerful agents of their own demise. Each massive new star emits a fierce torrent of radiation and stellar wind, and their eventual supernova deaths blast out powerful shockwaves. This feedback energy acts as a self-regulating mechanism, but its effects are wildly inconsistent. In some regions of the ring, this collective stellar fury might blow the remaining gas and dust clear out of the star-forming zone, effectively shutting down production in that entire sector almost overnight. In other areas, the feedback might actually trigger the next wave of star birth by compressing adjacent gas clouds, creating a domino effect of creation. The balance between these two opposing outcomes, triggering and quenching, is exquisitely sensitive to local conditions like density and magnetic field strength, leading to a patchwork of activity across the ring that averages out to a chaotic and unpredictable overall rate. We are witnessing a galaxy engaged in a constant, violent struggle between the forces of creation and destruction, a struggle whose outcome changes from 1 million-year period to the next. This erratic behavior makes the Cartwheel a crucial laboratory for understanding not just galactic collisions, but the very nature of star formation itself. Its fluctuations suggest that the process is not a simple, linear response to available gas, but a highly non-linear, self-interrupting chain reaction. The galaxy's history is not written in a steady hand, but in a frantic scribble of intense activity and sudden stops, a record of a system trying to find a new equilibrium after a fundamental trauma. By studying the timing and intensity of these bursts, astronomers can begin to decode the complex physics of feedback and turbulence, gaining insights that apply to the earliest starburst galaxies in the universe and helping us understand why the cosmos flickers to life in the irregular, beautiful, and unpredictable way that it does. Now, as we attempt to understand the Cartwheel's grand architecture, we must measure its motion, the fundamental spin that holds this cosmic wheel together. This brings us to a profound and puzzling discovery about its very dynamics, the anomalous rotation curve. In any galaxy, the way its stars and gas rotate around the center is governed by a delicate balance between the pull of gravity and the inertia of motion. By carefully measuring the rotational velocity at different distances from the core, astronomers can create a map of the galaxy's mass distribution, both seen and unseen. For a typical spiral galaxy, this creates a predictable curve. Velocities rise steeply near the center and then gradually flatten out at larger radii, a telltale signature of the immense, invisible dark matter halo that envelops the visible disk. But the Cartwheel Galaxy is not typical, and its rotation curve is anything but predictable, presenting a bizarre profile that defies our standard models and hints at a gravitoscape twisted by colossal violence. When astronomers painstakingly charted the rotational speeds across the Cartwheel's vast expanse, they anticipated a curve that would at least roughly follow the classic flattened shape, even if distorted by the collision. What they found was a chaotic and erratic profile. The velocities do not follow a smooth, logical transition from the core to the ring. Instead, the curve exhibits strange plateaus, unexpected dips, and sudden spikes. In some regions, the gas is moving far slower than the combined gravity of the visible and dark matter would dictate. In other pockets, it is racing along at velocities that suggest an overwhelming and strangely localized source of gravitational pull. It's as if the galaxy's rotation is being governed not by a single, unified force, but by a series of conflicting, invisible hands tugging in different directions. This anomalous curve is a direct and powerful testament to the disruptive power of the collision. A galaxy's rotation is a deeply ingrained property, a relic of its initial angular momentum billions of years ago. The head-on impact that created the Cartwheel didn't just rearrange its stars, it delivered a catastrophic gravitational shock to the entire system, violently stirring its orbital dynamics. The orderly, circular orbits that characterized its past life as a spiral galaxy were thrown into chaos. The result is a system where different components, the ancient stars in the core, the newly formed stars in the ring, and the vast clouds of gas are all trying to settle into new equilibrium states, their motions reflecting this recent trauma rather than a long-held stability. The rotation curve is not a clean map of mass, but a messy recording of this gravitational recovery process, a snapshot of a galaxy whose parts are all moving to the beat of a different drummer. The most compelling explanation for these rotational discrepancies lies in the profound disconnect we discussed earlier between the visible matter and the dark matter. Our models assume these two components influence each other seamlessly through gravity. But in the cartwheel, the visible matter has been violently reorganized into a sharp, expanding ring, while the dark matter halo remains a smooth, undisturbed sphere. This creates a situation where the gravitational anchor for the rotating material is not where it appears to be. The stars and gas in the ring are spinning rapidly around the galactic center, but the primary source of the gravity holding them in their orbits, the dark matter, is not concentrated in the ring with them. Its pull is emanating from a much broader, more diffuse region. This mismatch between the location of the mass and the motion it dictates could easily produce the strange kinks and plateaus observed in the rotation curve, as the visible matter responds to a gravitational field that is out of sync with its own brilliant structure. Furthermore, the incredible violence of the starburst itself adds another layer of complexity. The relentless energy from countless supernova and stellar winds within the ring is not just creating light, it is generating immense pressure, physically pushing against the surrounding gas and altering its dynamics. This feedback effect can act as a counterforce to gravity, effectively propping up the outer regions of the ring and allowing the gas to maintain higher rotational speeds than it could through gravity alone, or conversely, creating turbulent pockets that slow down the motion in unexpected ways. The anomalous rotation curve, therefore, is not just a puzzle to be solved. It is a unique window into the real-time interplay between the two most powerful forces in the universe, gravity and raw energy, locked in a complex dance that continues to shape the cartwheel's destiny. Nestled within the cartwheel's brilliant ring, like sapphire jewels set into a celestial crown, are isolated pockets of light so intensely blue and so anomalously bright that they defy easy classification. Astronomers call them blue blobs, and these mysterious objects are far more than just especially bright star clusters. While they appear at first glance to be simply dense knots of young, hot stars, a deeper look through spectroscopic analysis reveals a set of spectral signatures and brightness patterns that simply don't align with any known type of stellar congregation. Their light tells a story that is both familiar and utterly strange, forcing us to consider that we might be looking at an entirely new class of cosmic object born from the galaxy's unique, violent conditions. The first and most obvious anomaly is their sheer, overwhelming luminosity. These blobs outshine even the brightest and most massive globular clusters known to exist, radiating with an energy output that is difficult to reconcile with a standard collection of stars. If these were ordinary star clusters, the number of massive, blue O-type and B-type stars required to produce such a brilliant and concentrated glow would be almost unimaginably high, pushing the limits of what we believe is physically possible for a single gravitationally bound structure. This excessive brightness immediately suggests that either our understanding of how stars form and congregate is fundamentally flawed, or that these blobs are powered by something more exotic than just a high concentration of young suns. They are cosmic lighthouses blazing with a light that seems to demand a special explanation. The plot thickens considerably when we analyze their light through a spectrograph, breaking it down into its constituent colors like a cosmic rainbow. The spectra of these blue blobs are a chaotic tapestry of conflicting signals. They show the strong, broad emission lines expected from the seething hot gas of a furious starburst region, but these lines are often shifted, widened, or superimposed in ways that indicate tremendous velocities and violent motions within the gas. In some blobs, the spectral lines hint at the presence of shock waves, the telltale sign of material slamming into other material at supersonic speeds, which is more typical of a supernova remnant than a serene star cluster. This spectral pandemonium suggests an environment of incredible turbulence, where gas is not simply glowing from starlight but is being heated by powerful, disruptive forces from within. One compelling theory posits that we are not looking at single clusters, but at a rare and transient stage of galactic evolution, the birth of dwarf galaxies within the ring itself. In this scenario, the expanding shockwave compressed not just gas to form individual stars, but entire, gigantic clouds of gas massive enough to collapse under their own gravity and form self-contained galactic embryos. These tidal dwarf galaxies would be small, independent systems in the process of being born, with their own intense galaxy-scale starburst lighting them up from within. This could account for the incredible luminosity and the complex spectra, as we would be witnessing all the chaotic physics of galaxy formation, violent star formation, stellar feedback, and gravitational settling playing out in a tiny, isolated pocket within the larger ring. The blue blob would be a galaxy within a galaxy, a unique and short-lived phenomenon. An alternative and equally fascinating explanation is that we are seeing the effects of a superstar cluster in its earliest and most violent phase. This is a cluster so dense and so rich in massive stars that their collective energy output creates a unified superwind. The radiation and stellar winds from hundreds of thousands of massive stars combine into a single, catastrophic outflow that slams into the surrounding gas, creating a massive bubble of shocked, glowing material that envelops the entire cluster. In this view, the brilliant blue light of the blob comes not just from the stars themselves, but from this enormous, superheated envelope of gas that has been energized by the ferocious activity within. The unusual spectra would then be a direct result of this intense feedback process, a signature of a stellar nursery so extreme that it is effectively blowing its own roof off, making it appear as a single, coherent object of phenomenal brightness. The mystery of the blue blobs encapsulates the essence of the Cartwheel Galaxy itself, a place of extreme physics and beautiful contradictions. They are either the smallest galaxies or the largest star clusters, objects that challenge the very definitions we use to categorize the cosmos. Their existence provides a stunning glimpse into the creative power of galactic collisions, demonstrating that such events can forge not just new stars, but entirely new types of structures that push the boundaries of our understanding and remind us that the universe always has new wonders to reveal. This absence of radio jets is particularly baffling because other lines of evidence strongly suggest a supermassive black hole does indeed reside at the Cartwheel's heart. The erratic flickering of the core's brightness, the immense gravitational pull needed to hold the entire structure together, and the very nature of galactic cores all point toward the presence of a massive central object. In most galaxies, a black hole of this size would be expected to announce its presence with powerful, bipolar jets shooting out for thousands of light years, visible as brilliant tendrils in radio telescope images. The fact that we see nothing but silence is a contradiction that forces us to reconsider what we know about how these cosmic engines operate. One of the most compelling explanations for this radio quietness is a simple but profound lack of fuel. A supermassive black hole is only as active as the material it can pull in. To power the intense magnetic fields and relativistic particle beams that create radio jets, the black hole needs a steady and abundant diet of gas, dust, and stars. The same colossal collision that reshaped the Cartwheel may have effectively starved its central monster. As the intruder galaxy shot through the core, its gravitational pull would have acted like a cosmic vacuum cleaner, sucking up and flinging outward the vast reservoirs of gas that once swirled around the galactic center. This would have left the central black hole isolated in a relative vacuum, a king without a kingdom, unable to accrete enough material to switch on its most powerful and visible output. Another fascinating possibility is that the black hole is not entirely dormant, but is feeding in a fundamentally different mode. Instead of accreting material in a smooth, steady disk that can power organized jets, it might be consuming gas in messy, chaotic chunks. Imagine the difference between pouring a steady stream of sand onto a funnel, which creates a smooth flow, versus dropping in large rocks one at a time, which clogs and disrupts the process. If stars or large gas clouds are falling in sporadically, the accretion process could be unstable and inefficient, generating flashes of light and X-rays but failing to produce the sustained, focused energy needed to launch and maintain those colossal radio jets. The black hole might be sputtering instead of roaring. The environment around the black hole itself could also be suppressing jet formation. The powerful radio jets we see in other galaxies require not just abundant fuel, but also incredibly strong and well-ordered magnetic fields wrapped tightly around the black hole's poles. These fields act like the barrel of a gun, channeling and collimating the energetic particles into tight, focused beams. The gravitational cataclysm that disrupted the cartwheel may have utterly scrambled these magnetic fields, leaving them weak, disorganized, and tangled. Without this precise magnetic architecture, any energy released by accretion would simply dissipate as a weak, undirected haze of radiation, a faint puff of steam instead of a laser beam, rendering it invisible to our radio telescopes. This would mean the black hole's silence is not a sign of inactivity, but a testament to the sheer disruptive power of the collision, which reached into the galaxy's very heart and disabled its central engine. But the echoes in the cartwheel are far from ordinary. They exhibit bizarre and beautiful patterns that are key to unlocking its hidden architecture. When a supernova erupts, it sends out a flash of light in all directions, much like a camera's flash in a vast, dusty room. The initial pulse of light travels directly to our telescopes, but that's only the beginning. Some of that light travels on a longer, indirect path, striking vast clouds of dust that are otherwise invisible to us. This dust absorbs the high-energy ultraviolet and X-ray light from the blast, and then re-emits it almost instantly as a delayed, visible glow that we can see. This secondary pulse, arriving months or even years after the initial flash, creates a luminous echo that appears to expand outward from the explosion site at impossible, faster-than-light speeds. Of course, it's not actually moving faster than light. It's an illusion of perspective where the light from more distant parts of the dust cloud takes longer to reach us, making the echo appear to travel across the sky. Within the Cartwheel Galaxy, these echoes are not forming the simple, expanding spheres or rings we might expect. Instead, they are twisted into complex, overlapping arcs and strangely shaped wisps that look more like celestial graffiti than perfect geometry. This distorted morphology is a direct map of the galaxy's secret dustscape. The unusual shapes tell us that the dust clouds illuminated by these supernovae are not smooth or uniformly distributed. They are clumpy, filamentary, and full of vast cavities and tunnels carved out by the fierce stellar winds and radiation from previous generations of massive stars. Each unique echo pattern is essentially a flashlight beam revealing the intricate, three-dimensional structure of the interstellar medium in that particular region, a structure that would otherwise remain completely hidden from our view. By meticulously tracking the evolution of multiple light echoes from different supernovae across the ring, astronomers can perform a kind of cosmic tomography. They can stitch together a detailed, three-dimensional model of the cartwheel's dust distribution, revealing not just where the dust is, but how it's arranged on a grand scale. This has unveiled another layer of the collision's legacy. The dust is not smoothly spread throughout the ring, but is concentrated in enormous, swirling tendrils and colossal, hollowed-out bubbles. These structures are the direct result of the starburst's feedback, showing us how the furious energy of newborn stars is physically sculpting their own environment, creating a labyrinth of gas and dust that will dictate where the next generation of stars can and cannot be born. The light echoes are therefore more than just pretty patterns. They are dynamic probes, allowing us to see the invisible scaffolding of the galaxy and understand how its most violent events continue to shape its future. And now we turn our attention to a molecular mystery, one that involves a gas that is fundamental to the very process of building stars. Across the universe, cold clouds of molecular hydrogen are the raw material for stellar birth. But hydrogen is notoriously difficult to detect directly. Instead, astronomers use carbon monoxide as a tracer, a reliable stand-in that reveals where these vast, cold reservoirs of star-forming gas are hiding. In most galaxies, the distribution of carbon monoxide follows a beautifully logical pattern. It's densely concentrated in the spiral arms and active stellar nurseries, its presence a perfect map of where the next generation of stars will ignite. But in the Cartwheel Galaxy, this logic completely breaks down, presenting us with a distribution so strange and counterintuitive that it challenges our core understanding of how galaxies produce new suns. When researchers mapped the Cartwheel's carbon monoxide using powerful radio telescopes, they expected to see an intensely bright, coherent ring mirroring the brilliant blue ring of young stars. After all, that is where the starburst is happening. That should be where the fuel is being consumed. Instead, the map that emerged was a chaotic and disjointed patchwork. The carbon monoxide is not smoothly distributed throughout the ring. It appears in brilliant, concentrated clumps in some regions, while in other, equally active parts of the ring, it is startlingly faint or completely absent. Even more puzzling, significant reservoirs of this molecular gas were discovered drifting in the seemingly empty space between the ring and the galaxy's core, and in the quiet outer halo, places where there is no star formation occurring at all. It's as if someone went into a kitchen, found the flour and sugar stored not in the pantry but in the bedroom and garage, while the actual mixing bowls were sitting empty. This bizarre disconnect between the gas and the starlight points to a complex and violent history of how the raw materials of creation were handled during the collision. The most likely explanation involves the different behaviors of various gas phases during the impact. The initial shockwave that ripped through the galaxy would have treated the tenuous atomic hydrogen and the dense, cold molecular clouds very differently. The lighter atomic gas, being more fluid, was likely swept up efficiently and pushed outward to form the ring. But the dense, massive molecular clouds, the ones rich in carbon monoxide, may have behaved more like rocks in a stream. Their immense gravity and inertia could have allowed them to partially resist the smooth outward push. Some might have been shattered and fragmented by the shock, their carbon monoxide dissociated by the intense radiation until it could later reform in new, unexpected locations. Others might have been flung outward on chaotic, elliptical orbits, only to fall back inward later, creating those strange, isolated pockets of gas we now see drifting far from the main action. The environment within the ring itself then further complicates the picture. The regions that are now devoid of carbon monoxide aren't necessarily empty. They might be the sites of the most intense stellar activity. The fierce ultraviolet radiation from thousands of massive stars is a destructive force for molecules. It can photodissociate carbon monoxide, breaking the molecule apart and leaving the carbon and oxygen atoms to float alone. In these extreme environments, the very tool we use to find star-forming gas is being destroyed by the stars that gas created. The brightest carbon monoxide clumps, therefore, might not be the places where star formation is happening most fiercely right now, but rather the places where it is about to happen or where it has recently ceased. They could be pristine reservoirs of gas that the wave of star formation hasn't reached yet, or they could be the shielded cores of clouds that have survived the initial onslaught of radiation from their newborn stellar neighbors. This unusual molecular map forces a profound shift in how we view the Cartwheel's life cycle. It suggests the galaxy's star-forming engine is not running on a simple, full tank of gas. Instead, it's operating on an erratic and inefficient fuel injection system, with its raw materials scattered, hidden, and sometimes being destroyed faster than they can be used. The journey from cold, silent gas cloud to brilliant, new star is a delicate one, and in the Cartwheel, that path is more turbulent and less direct than anywhere else we've seen, revealing a level of complexity in galactic evolution that we are only just beginning to decipher. But just as we're beginning to map the full stellar population, our census reveals another glaring omission, a missing class of objects that should be teeming within the Cartwheel's chaotic nursery. When astronomers train their most sensitive infrared telescopes on the galaxy's star-forming ring, they expect to find a particular kind of resident in abundance, brown dwarfs. These are the universe's failed stars, objects that formed like stars from collapsing gas clouds but simply didn't gather enough mass to ignite sustained fusion in their cores. They are too massive to be called planets, yet not massive enough to truly shine, destined to spend their existence as dim, cool embers slowly fading into darkness. In a region of vigorous star birth, the laws of statistics demand that brown dwarfs should be everywhere, vastly outnumbering their brilliant stellar siblings. Yet in the Cartwheel, they are conspicuously, almost completely absent. This isn't just a minor discrepancy, it's a fundamental challenge to our understanding of how stars form under extreme conditions. The absence of these faint objects is particularly baffling because we understand the basic process of star formation to be a democratic, if not entirely fair, one. When a giant molecular cloud collapses, it fragments into clumps of various sizes. The vast majority of these clumps end up with very low mass, becoming brown dwarfs. A much smaller number gather enough material to become true stars. This ratio is so predictable that in most star-forming regions, from the Orion Nebula in our own galaxy to distant starbursts, brown dwarfs are a common, if dim, population. Their faint glow is a standard feature in deep infrared surveys. For the Cartwheel's ring to lack them suggests that something profound and unusual is interfering with the star formation recipe, skewing the results toward only the most massive and brilliant outcomes. It's as if a cosmic bottleneck has appeared, preventing the formation of smaller objects and allowing only the giants to be born. So what could be causing this peculiar bias? The leading theory points to the overwhelming and relentless environmental pressures within the ring. The star formation here isn't just happening, it's occurring at a ferocious, violent pace driven by the powerful shockwave that continues to expand outward. This wave doesn't just gently compress gas clouds, it slams into them with unimaginable force, creating regions of such incredibly high pressure and density that the normal process of cloud fragmentation is completely short-circuited. In a typical stellar nursery, a cloud fragments into a wide spectrum of clump sizes, but under the extreme conditions in the Cartwheel's ring, the cloud may be forced to collapse into only the most massive, dense cores possible, skipping the formation of smaller fragments entirely. The environment essentially sets a mass floor for star formation, dictating that nothing below a certain heft can come into being. Another compelling possibility involves the brutal effects of radiation and competition. The ring is already packed with massive, luminous stars that flood their surroundings with intense ultraviolet radiation. This fierce light exerts an outward pressure on the surrounding gas, effectively evaporating the raw material that smaller, budding stars need to grow. A protostar destined to be a brown dwarf, which begins with only a small reservoir of mass, would have its tenuous gas envelope stripped away by this radiation before it could even finish collapsing, snuffing it out before it had a chance to fully form. In this cosmic battlefield, only the largest, most aggressive protostars that can gather mass quickly enough can survive the blistering radiation bath from their monstrous neighbors. The brown dwarfs aren't missing, They are being aborted before they can ever draw their first breath, their potential existence erased by the very same firestorm of creation that gives life to the stellar giants. This missing population has significant implications for the galaxy's long-term evolution. Brown dwarfs, while dim, are long-lived and would normally contribute a substantial amount of mass to a galaxy's inventory. Their absence means the Cartwheel's total stellar mass budget is likely lower than our initial estimates, and the chemical enrichment of its future generations of stars will be different. Without countless brown dwarfs eventually shedding their outer layers and contributing their material back to the interstellar medium, the building blocks for future planets and stars will have a slightly different composition. The galaxy's current starburst is not just a spectacular but temporary event. It is a transformative episode that is fundamentally altering the demographic future of the entire system, creating a stellar population that is oddly top-heavy and missing the faint, numerous dwarfs that normally make up the silent majority of a galaxy's inhabitants. And this breathtaking cosmic distance, paired with the galaxy's own tremendous velocity, introduces our final and perhaps most mind-bending phenomenon, the strange relativistic effects that warp our perception of time within the Cartwheel. We are not just passive observers of this galactic drama, we are viewers watching a film playing in extreme slow motion, a consequence of the universe's fundamental laws that makes the frantic activity within the ring appear to unfold at an eerily delayed pace. This isn't an optical illusion. It's a direct result of Einstein's theory of relativity, which tells us that time itself is not a constant tick-tock throughout the cosmos, but a variable flow deeply influenced by gravity and motion. The primary effect at play here is known as cosmological time dilation. The Cartwheel Galaxy is not only 500 million light-years away, it is also rushing away from us at a fantastic speed due to the expansion of the universe. This immense velocity causes a Doppler shift in the light we receive, stretching out the wavelengths and making events appear to transpire more slowly from our vantage point. Imagine an ambulance speeding away from you. The sound of its siren drops in pitch, its waves stretched by the motion. Light behaves the same way. The frenetic bursts of star formation, the violent supernova explosions, the chaotic swirl of gas, all of these processes are actually happening at a normal rate within the galaxy's own frame of reference. But by the time that light has crossed the vast intergalactic void to reach our telescopes, the information it carries has been stretched and slowed, making the entire spectacle seem like it's moving through cosmic molasses. This time dilation creates a fascinating observational challenge. A supernova that might brighten and fade over a period of several weeks in its local environment could appear to take months or even years to complete its cycle from our perspective on Earth. This slow-motion view is a double-edged sword for astronomers. On one hand, it provides an incredibly detailed, frame-by-frame look at processes that are normally fleeting and difficult to capture. We can study the intricate expansion of a supernova remnant or the early evolution of a massive star cluster with a precision that would be impossible in a closer, faster-moving galaxy. It's like having a remote control for the universe with a permanent slow-motion button pressed for this one object. On the other hand, this same effect means we are never seeing the Cartwheel as it truly is in this present moment. We are witnessing its history. The light arriving at our eyes today left the galaxy during a time when life on Earth was just beginning to crawl onto land. We are studying a snapshot of its adolescence, a 500-million-year-old postcard from a past epoch. This incredible lag means that any change we hope to observe in human timescales is virtually impossible to detect. The majestic expansion of its ring, moving at 200,000 miles per hour, would appear to us to creep forward at an imperceptible snail's pace. This time warp creates a profound sense of cosmic patience, reminding us that some of the universe's greatest stories are not just told across vast distances, but are also stretched across incomprehensible spans of time, offering us a uniquely delayed but spectacularly detailed window into the workings of a galactic wonder. And so, after this incredible journey through 30 of the strangest phenomena in the Cartwheel Galaxy, what are we left with? We began with its breathtakingly perfect ring, a cosmic bullseye born from a violent, head-on collision that sent a shockwave rippling through the galaxy. We discovered the ghostly void where a massive central bulge should be, plucked away by the intruder's gravity, and witnessed the intense starburst clusters igniting like a chain of cosmic fireworks within that expanding wave. We hunted for the ghost companion galaxy, the culprit whose own stars were shredded and scattered, leaving behind only a faint remnant of its former self. We mapped the unusual, lopsided hydrogen distribution, a colossal envelope of gas flung far beyond the stellar ring, and pondered the profound radio silence that defies the very laws of astrophysics we thought were set in stone. We then marveled at the ultraluminous X-ray sources, those bizarre binary anomalies shining brighter than physics should allow, and were baffled by the case of the missing supernova remnants, the ghostly graves of massive stars that have seemingly vanished without a trace. We grappled with the strange behavior of dark matter, whose smooth, undisturbed halo stands in stark contrast to the rearranged visible matter, a disconnect confirmed by the subtle warping of background light through gravitational lensing. We decoded the ultraviolet ring paradox, the slight offset revealing the time it takes for stars to clear their dusty cradles, and observed the warm infrared halo, a vast cocoon of dust heated by the galaxy's own brilliant light. Our investigation uncovered high-velocity gas clouds moving too fast to be bound, a missing generation of intermediate-age stars that points to a long period of dormancy, and a chaotic magnetic field tangled and rebuilt by the violence of the starburst. We found a strange metallicity gradient with a metal-rich core and a metal-poor ring, a chemical fossil record of the collision's impact. We listened to the flickering, variable core whose irregular pulses hint at hidden activity, and we noted the uneven distribution of binary star systems clustered in the densest regions of the ring. We searched in vain for planetary nebulae, the glowing tombs of sun-like stars that seemed to be dying invisibly, and charted the erratic star formation rate, a volatile pattern of intense bursts and sudden lulls. We analyzed the anomalous rotation curve, a chaotic map of the galaxy's dynamics still recovering from the impact, and puzzled over the mysterious blue blobs, those intensely luminous objects that could be nascent dwarf galaxies or superstar clusters in their most violent phase. We considered the radio-quiet core and the potential supermassive black hole that refuses to announce itself with jets, and we used the beautiful, distorted patterns of supernova light echoes to map the hidden dustscape in 3 dimensions. We traced the unusual carbon monoxide distribution, finding star-forming gas in all the wrong places, and discovered the missing brown dwarfs, a population of failed stars seemingly aborted by the extreme environment. And finally, we recognized that we are viewing all of this through the lens of strange relativistic effects, watching a 500-million-year-old film in extreme slow motion due to the expansion of the universe itself. So what do these 30 mysteries ultimately teach us? They show us that a galaxy is not a static island universe, but a dynamic, evolving system whose history is written in violence and whose future is shaped by chaos. The Cartwheel Galaxy is a masterpiece of destruction and renewal, a place where the standard rules of physics are not broken, but are forced to operate under such extreme conditions that they produce results we are only beginning to comprehend. It teaches us humility, reminding us that for every answer we find, the universe presents 10 new questions. It is a single, magnificent laboratory that encapsulates the entire story of galactic evolution, from quiet maturity to catastrophic collision, and through to a violent, beautiful, and ongoing rebirth. Now we turn the discussion over to you. After hearing about these 30 strange phenomena, which one captures your imagination the most? Is it the ghost companion whose gravity sculpted this beauty only to vanish itself? The dark matter that felt the collision but did not respond, or the ultraluminous X-ray sources shining beyond their theoretical limits? Share your thoughts in the comments below. We read every single one. Your curiosity is what drives this journey of discovery forward. Thank you for joining us on this expedition to the edge of understanding. Remember to like this video if you enjoyed the tour, and subscribe so you don't miss our next voyage into the depths of the cosmos. Until next time, keep